Right, thanks. So there has already been quite a few discussions about LHC in this conference, so I will be reasonable, sort of brief on the LHC part and focus more on the beyond part. Okay, but let's start just with a simple summary of the current status of particle physics. So we found the Higgs. We haven't seen any other new physics yet. And looking into the future, the immediate future is right now and down the road for about 20 years. And it's called LHC run 2 to run 5, according to this table. And LHC has already started at high energy, and probably it's going to run at the energy of about 13 TeV, and it's going to get tens and ultimately hundreds more data compared to what's the LHC data we currently have. So, because of the increase of, mainly because of the increase of the center of mass energy, and also because of the increase of the amount of data we are going to collect, this is a impressive extension of the reach of new physics. So this is just some figures. That this is, I think this is the stop search, and this is gluino search, and so on. This is the limit you can set in the M-Sugra plane. So we frequently say, new physics, we haven't found a new physics because new physics is around the corner. If that's the case, we are going to turn a very big corner. So if the new physics could be just right there, okay? And what would happen, well, it could be just one of these, okay? So if any of these, so these are the so-called current accesses. If any of these is there, we'll immediately discover them quickly. And or just anything else just around the corner, we'll see very spectacular discovery at LHC. Now, but going forward with the accumulation of data, you see that so this is some estimate of how the mass reach of new physics as a function of luminosity. And so in this particular example, you take some new physics. For example, it's some new physics that run 1 has set a limit around 2 TeV. Okay, for example, this could be a pair production of 1 TeV gluino. So the characteristic of these kind of new physics is that it's actually reasonably strongly coupled, and the mass reach is basically set by you running out of event. So its production rate is similar to the standard model rate at the same kinematical regime. Okay, so in this kind of new physics, you see that what's going to happen is that you rapidly gain. There's a very rapid gain in the initial several inverse femtobarn. Sorry, this is the new reach versus the old limit at the ratio of new reach over the LHC run 1 reach. So you see there is a rapid gain at the first several inverse femtobarn, then there is a slow improvement afterwards. So the news in this coming year will be very exciting, and after that we have to be patient, basically, and for this kind of new physics. So this is basically because there's this well-known fact that because the PDF is very steeply falling. So yeah, that's the reason for this behavior. And if the new physics is not as strongly coupled, for example, if some kind of new physics run 1 can only set a limit around 500 GeV. So this is the kind of new physics where, the rate of standard model background is actually quite a bit larger than the signal. And in this kind of scenario, the luminosity actually plays a more important role. And so you will, it's actually reaching close to its full potential only after 30, 40, or maybe 50 inverse femtobarn of data. Okay. So let's see, what are some of those highlights? So I just give you some very brief examples. For example, we will be able to look for additional Higgs bosons. Okay, so is the Higgs boson we found the only neutral particle, the only scalar particle, or there are additional ones? Okay, so there will be solid gains at LHC, and there will be potential to make new discoveries. A discovery in this category will be very interesting because it could tell us maybe the nature of the electrical symmetry breaking is not a simple one that we have been assuming, or it will also give us a very new perspective on the world of fine tuning. If one scalar particle is already fairly tuned, two of them will be even more tuned. So again, this is a famous example. So if we can look for top partners in SUSY, look for stops, and the naturalness of the of SUSY is proportional to m stop square. So this again, the gain is proportional to the gain of proportional to the increase of center of mass energy. So well, I think if a discovery of top partner will be a stunning success of naturalness. On the other hand, if there's no discovery, of course, we'll push further. The SUSY will be even more tuned, proportional to the limit of stop mass square we are going to set. And there's a similar story in this compositeness story where in many models it requires the existence of a light top partner, basically correlated with the light Higgs mass. And so LHC 8 is already getting closer to the interesting top partner range in this simple class of composite Higgs models. And LHC 14 or 13 should actually cover the full range of it, at least putting very strong limit constraint on the simplest probably variants of minimum composite Higgs models. Okay, so just in general, I think LHC run 1, as we all see from these tables and also the summary talks earlier in this conference, LHC run 1 has pursued a very broad program of new physics, and it will certainly continue at run 2. And of course, there are gaps to be filled, a new signal to be looked at. A lot of things has been discussed, such as what if we have softer particles, we have displaced vertex, and what if the signal doesn't have leptons as a very hadronic rich, and so on and so forth. So my general impression, so I'm sure there are more things to discuss here, but my general impression is that the experimental collaborations are fairly on top of most of these things. So I have confidence that they will carry out a even more comprehensive program successfully. So that's my very quick summary of LHC. What are our expectations for LHC? But let me emphasize that even at the completion of LHC, there will still be many open questions. A lot of those very fundamental questions of particle physics that are left unanswered, and such as the nature of electron asymmetry breaking, naturalness, and dark matter. And also, a discovery at the LHC is unlikely to be complete. Okay, I'll elaborate on, for the rest of my talk, I will elaborate on each of this. Right? But because of this, we need to go beyond. We need to consider the next generation of experiment beyond the LHC. Okay. So for that, let me first, mention that there have been activities in recent years, in particular, thinking about what's the next step beyond the LHC in high-energy experiments. So there are many facilities being proposed. So there are these linear colliders, and also most recently there has been a lot of renewed interest in this kind of circular colliders, which is basically a scaled-up version of a LAP plus LHC. So it's, roughly speaking, consistent of a E plus E minus Higgs factory around 250 GeV. Central mass energy, and that proposal at CERN is called FCCEE. In China, it's called a CEPC, Circular Electron Positron Collider. Okay, this is a future circular collider. Okay, I'm sure that's not the official name of the collider if they're getting built. So it cannot be future, but anyway. And there's also later on it will be followed by a PP version, roughly around 100 TeV. At the CERN, it's called FCCHH. In China, it's called SPPC. Okay. Super proton-proton collider. Okay. So for the rest of my talk, and I'm going to focus more on these later options. Although you see the sum of the lessons, especially the Higgs factory phase, can directly be extrapolated to the ILC, for example. Okay. So since I'm more involved in in the Chinese side of the effort. Let me just give you also a very brief update of the status, what's going on in China. And so there is a preliminary conceptual design report, very preliminary, and that has been finished, and it contains two parts. One part is, basically three parts. One part is about the accelerator design, and then there is a volume discuss the physics case, and also there is a lot of discussion in some preliminary detector design. It focuses mainly on the Higgs factory, and if you want to look at it, here's how you find it, and they are proposing for R&D funding at this moment. So the proposal has been submitted, and the aim is they're aiming at getting into being part of this so-called 13th five-year plan. So for those of you not coming from a communist country, so this is their main funding instrument in communist countries, started by Soviet Union, I believe. So, and they're also exploring other sources, but this is their main thrust. And I think, most optimistically, it's very hard to tell right now. It's very preliminary, but the most optimistically, we probably will be able to see EE collision at the early 2030s. Okay, so let's talk about the capability of these future colliders. So at the E plus E minus Higgs factory, the main gist is that it actually is a very clean environment, and it's very, very good for precision measurement. Okay, you measure very small deviations from the standard model predictions, which can be parameterized roughly in this form, which is the V square over the mass scale of new physics square. And for example, if we can look at the Higgs coupling, so LHC ultimately will push a lot of those coupling into the range of 5 to 10%. And this means that this roughly translated into a LHC through this kind of measurement will be sensitive to a new physics scale around the TeV. Okay, at the same time, obviously, LHC can direct search these new physics as well. On the other hand, in order to go beyond the LHC, so based on this kind of argument, we really need to push a lot of those precisions down to 1% or less, basically. So now you're actually going above TeV and going also above the reach of LHC direct searches. And so, for example, this is what the Chinese proposal, so the CEPC can do. So there are some, for example, the flagship measurement is the Higgs Z coupling. This through the so-called recoil mass measurement, model-independent measurement of the Higgs coupling to Z, and this can be done very well to a sub-percent level, and many other coupling down to a percent level. So the gray bars are the percentage accuracy from high luminosity LHC, by the way. So this is a log scale too. And there is also a model-independent determination of the Higgs width, and so on and so forth. And all these things are, at the lepton collider, the precision is systematically dominated. So the European version, FCCEE, is aiming at a roughly twice higher luminosity. So we can just take a square root 2 of both. Basically, we can just take a square root 2 of these error bars. And also remember that the one important stage of any E plus E minus collider is that it can also run on the Z pole. This is a LEP1 phase, for example. And it will produce a lot of Z's and do precision measurement. Okay? So going from LEP to the new generation of Higgs factories, both FCCEE and the CEPC, you'll gain roughly a factor of 10 in terms of S&T measurement. Okay, so historically, this is a very successful venue for learning physics. So LEP1 plus LSD taught us a lot, okay, so about the standard model physics. I think we will learn, well, if this goes forward, we will also learn a lot more from this kind of precision measurement. I'll have a few examples later. Okay. Now, at the 100 TeV PP collider, and obviously, the increase of the biggest increase is just coming from the increase of central mass energy. And so these are just some production rates of some new physics. So the lower curves are LHC 14, and the upper curves are on the 100 TeV collider. Just from this production rate, you see that there is a huge increase in physics range, and which is can be demonstrated. Sorry about missing this figure. So it's demonstrated in many of these cases. So this is a SUSY search. This is just a simple Z prime search, and this is some hadronic resonance searches. So basically, you increase the mass reach roughly proportional to the increase of center of mass energy. Okay? So now earlier I begin my talk about mentioning this list of questions that LHC cannot really address very well. So let's see. Now I briefly summarize the capabilities of the new generation of colliders. Let's see how those things can translate into answers can help us answer those questions. So let me begin with the nature of electroweak symmetry breaking. Okay, so we often have the impression that this is very simple. So this is the Mach second hat potential. This is something that h squared plus h to the fourth. It's very similar and motivated by the Landau-Ginzburg theory of superconductivity. And Higgs goes down, gets a wave, and so on and so forth. However, I think this simplicity is very misleading because, first of all, just even very simple, and these numbers, we sort of have an idea what they are within this simple model. On the other hand, they are not predicted by any theory. We don't know how they got their values. So this cannot be the complete picture. So just at a very basic level. But moreover, okay, we actually know very little about the Higgs. Okay, so this we think we know it's a Mach second hat, but we actually don't. This is what we really know. We know that it's away from the origin, and we know a little bit about the potential around it. Okay, this is what we know. In particular, I can have these two very different looking potential. Okay, this is the Mach second hat. This is not. Okay, this is some other hat, and but they all give you the same answer that what we know now. Okay, and very interestingly, so for example, the difference between these two can get into a very important question. For example, is the electroweak phase transition first order or not? Okay, so this is a difference that LHC cannot distinguish. Okay, just this very elementary question. Without any, we want to know the full shape, full Higgs potential, and LHC is unlikely to tell us the answer. Right. So now just. I should be standing closer. So just in case you think I'm just making up these potentials, it will be very crazy to have these potentials. It's not. These kind of potential actually can happen in a very, very simple series. So for example, if I just write, just add a singlet to the standard model and write this kind of general couplings, you can already see that for example, this kind of interactions will generate that h to the 6 terms, okay, and leads to the shift of the triple Higgs coupling. So a generic estimate you can make based on this very simple potential tells you that if I am in this green potential, okay, namely the one that have the first order phase transition, it generically leads to the conclusion that it will shift. The Higgs and the Z coupling will be shifted from standard model prediction to at least 0.5%, and it generally leads to a order 1 shift in the triple Higgs coupling. And of course, so let's remind ourselves this is the precision that we can get from the Higgs Z coupling and the sub-percent, and 0.1 something percent. And then this is the accuracy we can measure Higgs triple coupling at 100 TeV PP collider. Okay, so you see that both of these are within the reach of the next generation colliders. So the bottom line is just the next generation collider combining these two measurements can already give us a lot of knowledge to distinguish this red versus this green. And we can even talk about directly looking for the singlet at the 100 TeV PP collider, and the production rate is actually fairly decent. We can probe the singlet close to a TeV in mass. Okay, so again, this is the bottom line. The combination of Higgs factory and the 100 TeV PP collider can actually go very long way to understand the nature of electroweak symmetry breaking. Okay, now let's come to naturalness. And so the first point is very obvious. So again, the 100 TeV PP collider can push much further our limit on naturalness. So again, this is the stop story, and the tuning proportional to the stop square. And it's therefore at the 100 TeV PP collider will gain roughly 2 order of magnitude in terms of constraining the fine tuning. And moreover, if the standard the MSSM is a little bit attuned, but then so the top partner is a little bit heavy, such as a 6 TeV, it can actually be discovered by the 100 TeV PP collider. And there is also composite Higgs model. So let's consider composite Higgs model. First of all, we can composite Higgs model predict a lot of these deviations. For example, the deviation from the Higgs Z and the Higgs W coupling on the order of V square over F square. F is the sort of the characteristic scale in the composite Higgs model. And it also predict give a prediction of the deviation in the S parameter, for example. So the precision measurement at the Higgs factory, both on the Higgs coupling and S parameter, can give you very good probes of this scale already. Okay, even before the running of the PP collider. Okay, so notice this is getting into very high scales in this parameter F, where for the natural composite Higgs models, people usually talk about some scale from 600 GeV to maybe a little bit more than TeV. Okay. We can, of course, direct search the composite resonances. So composite theory will have a lot of resonance, just like QCD have a lot of resonance. So this is the reach of at LHC, and this is the reach of an SPP, 100 TeV PP collider. So they're plotting for FCC, and so they may not look too different until you notice that this is the scaling of the x-axis is different. Okay, so this is so this is going much further. Okay, but again, that's not surprising. This is just basically a scale with central mass energy. Okay. So this combination of Higgs factory and the high energy PP collider again give you very strong probe in this composite Higgs scenario. Now, even at this moment, we haven't seen any top partners. This already motivated by a lot of us to make a top partner completely hidden. Okay, so this is the talk Gustavo gave yesterday, and one of those scenarios is called twin Higgs. So I think in this case, the top partner is neutral. It only couples to Higgs. And LHC reach is very poor. This is, if you want, this serves as an example of we could actually see nothing but at LHC, but the series is still completely natural at LHC. On the other hand, these kind of the irreducible, there's an irreducible contribution from this kind of new physics to the Higgs coupling to the Z, and that actually can be tested at the Higgs factory pretty well. So this actually, Higgs factory can probe this model in a non-trivial way, just by measuring the coupling, the deviation in the coupling between Higgs and Z. And I think Gustavo also talked about the folded SUSY, and that also the top partner does not have color. Oh, sorry. And this actually. In this case, actually, is the electroweak precision measurement give the strongest constraint. That can set a limit on this kind of top partner to roughly around the TeV scale. Okay, so the last topic the main physics question I'm going to talk about is dark matter, and I'm going to focus on this so there are many ways of looking for dark matter. Dark matter could also come with spectacular signals at the colliders, but let's just focus on this very basic channel, which was also mentioned yesterday. And it's already been pursued at LHC, which is the mono X channel, such as mono jet and so on. Moreover, I'm going to focus on mono jets, since that is usually giving you the strongest limit. And we can, so for example, this is the mono jet reach on the SUSY Wino-like dark matter, or in the SUSY Higgsino-like dark matter. So to just guide your eyes, sorry, this is the ultimate reach of LHC, high luminosity LHC, and this is the reach at 100 TeV PP collider. So just to guide your eyes, what is the mass we're talking about? If you, to get the correct thermal relic abundance, the mass of WIMP should be really in the TeV range, okay? So roughly at around the TeV range. So LHC limit on this is very limited. LHC reach of monojet is very limited because it is a very difficult channel. And the 100 TeV collider does get you into a lot of this interesting parameter region. And moreover, there is this interesting channel called disappearing tracks in particular for the Wino dark matter. And basically it's looking for a charge that Wino produced, then decay, going through several layers of tracker and then decay. Okay, so this is actually, for the Wino case, is setting a fairly interesting limit at the LHC already, which is 250 GeV. And this to be compared with the monojet limit at LHC at this moment, which is 0. Okay, so this is very impressive, and a naive scaling of those limits is you can show that at the 100 TeV collider, you can almost completely cover the Wino parameter space. Okay, so this is a summary of the monojet reach of dark matter. So the blue ones are the LHC reach, the red ones are the 100 TeV collider reach. You see that, remember again, we want a WIMP in the TeV range, is the 100 TeV collider really get us into that range, the interesting parameter range. And if we are considering slightly more elaborate models where you actually can produce the heavier electroweak charged particles, and then they decay down to dark matter, we can even enhance the reach significantly. Okay, so let me just, okay, okay, good. So the last thing I wanted to address is the LHC discovery scenario. So if we made a discovery at LHC run 2 or run 2, run 3, run 4, okay, so if we do that, is it possible that we can discover everything at LHC? Okay, so I think that would be great. However, I think it's highly unlikely. So just because we haven't seen anything yet, and if we really think about any of these big new physics scenarios, there is usually a at least order 1 spread of the spectrum. Just combine these two facts, it's unlikely we will discover everything, in the new file for anything. So just because we haven't seen anything yet. Okay, therefore, in this case, I think LHC discovery itself is not complete, and it will set a stage for future PP colliders. So it's just to give you a simple example, this is a random SUSY model for no reason. Okay, this is just if I pick random numbers in the spectrum, this is what it looks like. Just for this particular model, for example, this is the current limit. Okay, and LHC will discover gluinos, squark, and so on, some of the charginos, but it will not discover the rest of it. So this is, again, an example of an incomplete discovery. And moreover, even for the gluino, LHC will only produce a little bit of them, and going to 100 TeV collider, you will produce more than 3 order magnitude more gluinos. This, really give you opportunity to study gluino properties in detail, the precision measurement, okay, of the gluino. The composite Higgs model is the same story. Usually we're talking about order TeV split in the spectrum. So it's unlikely we'll discover the whole thing. Okay, so I'll conclude. And so LHC run 2 and go further will actually further probe new physics. There are interesting gains in reach. On the other hand, I think even at the end of LHC, there will be several very important fundamental questions in particle physics that cannot be answered fully by the LHC result, such as the electric symmetry breaking, naturalness, dark matter, and there are many more. Okay? So going beyond the LHC, I think there have been many activities recently in the community, particularly in the last couple of years, motivated, stimulated by the discovery of the Higgs. And there has been, as we have seen, the physics case is great, and there are many efforts underway to make it happen. So, okay, sorry. Thank you.
We have time for questions.
So in the search for dark matter colliders, there are two things that count. One is the mass, as you said. The other thing is the coupling. So the LHC, okay, in terms of mass, is correct what you say, but in terms of coupling with the high luminosity, it could go quite down in the, in the smallness of couplings that it can measure. So what about the colliders? I mean, the light...
100 TeV collider can only improve on that, right?
Right.
For any given mass and coupling, you'll produce more of them at the right. So far the candidate I have studied here have very standard couplings. So they are just SU2 gauge couplings because these are Wino and Higgs-Zenos. So they're So yes. So if you want to talk about smaller couplings and so on, I think going to higher energy you can only gain a lot. And yeah.
Okay. Thank you.
More questions? Well, if not, then let's thank the speaker again.
Thank you.